All right. So now we're going to actually wrap up our discussion about option strategies, and then we're going to try to at least get started with the Black-Scholes model, which is really um, one of the more important topics we'll be looking at in this course. So first, let's go back and revisit what we were doing last time in section 5. And you'll remember that we started to introduce option strategies. And so basically, we're going to consider two basic types of strategies: spreads and combinations. And so the way this works is that spreads are set up by creating or combining either two or more calls or two or more puts. It's not going to be both. That's the key to the whole thing. Either you have two or more calls, and it could be any number, but two is often the number that you'll see in one of these positions. And then if not two calls, it could be two puts, because often a position that's created with two calls will be very similar to the same exact position set up with two puts. The main difference might be the cost of the position, or maybe the maximum profit will be a little different, but it's basically the same logic in both cases. So with a spread, we have two or more calls, or else we might have two or more puts. Now, that being the case, though, obviously it wouldn't make any sense to simply buy two of the same call or two of the same put. So what this means is that they're going to need to be different somehow. So typically, although not always, the calls or puts have the same underlying asset and maturity date, but most likely they'll have different exercise or strike prices. That's really where a lot of the strategy is coming from. It's a question of where do you put those strike prices? And that, of course, depends on what you're trying to accomplish. So now, if you do have instead different assets or different maturity dates, then you're looking at a different type of situation anyway. So they would not normally fall into this category. So going forward, we'll just assume that in each of these cases, we always have the same asset, the same maturity date with different strike prices. Now, another thing that could be different, though, is that some of the options in a spread may be purchased and some may be sold, but not necessarily. Might be that you buy one and sell the other. It might be that you buy them both. You might sell them both. So there's a lot of possibilities here. So as you can probably imagine, the number of possible trading strategies with options is, let's just say, only limited by our imaginations. It's a huge number of possibilities. So we're going to look at some very basic approaches to trading options and creating positions that match up with our expectations of what's going to happen in the market in the future, because all of this is ultimately driven by what we expect to happen in the future. And what we're basically trying to do is put ourselves in a position where if that happens, we'll make money. Okay, so really short that a stock is going up tomorrow. You want to be in a position where you'll benefit from that if it does happen. Okay, so in other words, you're betting on your outlook on the market. So we have a couple of possibilities here. Oh, I almost forgot to mention combinations consist of at least one call and at least one put. And again, they typically will have different strike prices, although they don't have to, because it's a call and a put here. They could actually have the same strike price. So, but often they have different strike prices. But as again, we'll see that we probably will be assuming that the asset is the same for both options and the maturity date is the same. Because if not, it makes things a lot messier, and it maybe it isn't even a spread anymore or a combination. So that's what we'll stick with here. Okay, now that we got that straight, the spreads we want to look at are the bull, bear, and butterfly spreads. And that's again because these are very popular choices in the options markets. So we've already actually looked at the bull spread. And keep in mind too, since a bull or a bear spread be created either call puts. In order to make sure we know which is which, we often specify in the title whether it's a call created with calls or puts. So in other words, the title is designed to reflect this. For example, a bull spread created with calls is often referred to as a bull call spread. Well, that's pretty common sense. And then of course, if we set it up with puts, a bull spread created with puts would of course be a bull put spread, of course. Just so you know which. All right. And again, the choice isn't that important. It can work either way, but it will affect the cost of the position, the maximum profit, and the minimum profit. All right. So as we saw last time, with a bull spread, the position consists of buying the lower strike call, I mean, another or option, I should say, depend because it could be either calls or puts, and selling the higher strike option. In other words, assuming that the two options that we chose have two different strike prices. So we're going to buy the one with the lower strike price, or we're going to sell the one with the higher strike price. Okay. So that's a key, the buy low, sell high. Think of it that way. And what does that get us? Well, if you look at this graph that we put together, now this is based on these two IBM stocks. And if you want to go through the calculations, this table has the payoffs for the call. In this case, it's the low strike call and the high strike call that we sold. If you notice, this one is negative because we sold it. This one is positive because we bought it. In neither case, the payoff is always the spot price of the asset minus the strike price, or zero, whichever is greater. Then at the end, we put them together. We come up with a graph of just the payoff, which looks like this. But then when you take into account the cost of the position, you see that you can lose $1 because that's the cost of the position. If the stock price goes up, of course, we'll start to make money, but unfortunately, our profits are capped at $2. And that's because this is a very inexpensive position. If you just bought this low strike call, it would have cost you $3. By selling the high strike call, you've reduced that from $3 to $1, which is a 2/3 reduction, which is not bad. And that affects the rate of return that you'll get from this position. Now, it turns out that the bear spread is just the reverse of the bull spread. Okay. So in other words, and one more thing we need to pay attention to here. The bull spread is set up to benefit from a relatively small increase in the price of the asset. With a very low cost. Okay, if we really thought that the price might continue to rise, we probably would have just bought the low strike call in the first place. And then there would have been no point in selling the high strike call because that's what causes us to have a cap on our profits. Okay, so I have to think about where we think the stock is going. And of course, when we say where is it going, we mean by the maturity date of these options, which is usually very close. In other words, if this option or these options mature in a few weeks, well, really, we're thinking not in terms of the long run, but where the stocks are likely to go in the next few weeks. That's really what we're betting on. So anyway, yes. So we think this is a bullish position, meaning we're somewhat optimistic about the future direction of the stock. But a bear spread results from taking the opposite position into calls or puts. In other words, with the bear spread, we are buying the high strike option and selling the low strike option. And that's how we're reversing it. So we're actually expressing our view that the opposite will happen, meaning that we think the price will go down, not up. So we did exactly the opposite. We bought the high strike option and sold the low strike option. And if you look at the graph, the results for that, let's jump ahead a little bit here. You'll see, um, there it is, that yeah, like, I mean, you can see it's just this, it's been flipped upside down. In fact, I'll tell you what I'm going to do so you can see it better. I'm going to copy this into the notes. All right, we'll see how long that takes. There we go. So there's the bear spread. The corresponding bull spread looks like this. Here it is. Here it is. In fact, you know what I should probably put them next to each other from left to right. It might be even more instructive, but then they'll be really tiny. All right, so you can see, well, all right, you can kind of see them together. See if I can shrink up this page. All right, well, that's not too bad. But you should be able to visualize that what you've effectively done is taken the bull spread and flipped it upside down to turn it into a bear spread. And that's because we reversed the direction of the two options. So the one on the top is betting on the price going up, although only is to a certain degree. One on the bottom is betting on the price going down. If we thought it might go down further, then we probably would simply bought the high strike call and um, sold the high strike call, let it go with that. All right. Anyway, so those are bull and bear spreads. Now, the butterfly spread is a little bit different because we're trying to do something that is not possible with any other assets in the economy, as it turns out. The butterfly spread is fairly complicated. So what you have to do here is this. And now, just like with the bull and bear spread, we could create this with calls or puts. Let's just assume that we're doing this with calls. So I'll call it a butterfly call spread so we know that we're using calls. Oh, that's right. I remember I shrunk up the page. I was wondering why it got so small all of a sudden. All right, so here what is happening is this. And we have to visualize not two, but three strikes or options. So we have to assume the existence of, there are three, let's say there are three call options available on an asset. In the slides, they're talking about IBM stock. Okay, and we'll just call them one with a low strike, one with an intermediate strike, and a high strike. Now, in practice, if these are written on stocks, there's probably going to be dozens of strikes available. So it's not too much of a stretch to assume that there's three available to us. And so we'll call them low, intermediate, and high. And then what we're going to do is buy low and high strike calls or options. In this case, we're assuming calls. But then we're going to do something different. We're going to sell two of the intermediate strike calls. Wow, that's different. So when you see the graph, you're going to be very surprised, I think. And this is the result. Once you take into account the cost of the position, it looks like this. Now, you're probably wondering what in the world is going on here? What do we expect to happen? Why are we doing this? Those are all very good questions. So what's happening as soon as it's ready, is we'll see that we're hoping that the stock stays right here in the center. What we're doing here is we're betting against volatility. The word volatility means that the price fluctuates a great deal over time. So think of this as a bet against volatility. In other words, we're betting that the stock price stays right where it is at 50. We're assuming, by the way, I didn't mention that, but we're assuming that the stock price is currently at 50. So we're saying, listen, we think it's going to stay there, or at least very close. So we'll set up this position. And if we're right, if it stays in that neighborhood, we'll make some money. The only thing that can happen that can go wrong is if the price either suddenly starts moving up or down. And even then, there's a distinct limit to how much we can lose. The position only costs $1, so therefore we can only lose $1. On the upside, we can make up to $2. Okay, so that's our butterfly spread. In this case, it's a butterfly call spread. So now volatility, if you have some statistical background, volatility for financial assets is often measured as the standard deviation of the returns to the asset. Okay, so it's not so surprising after it's the returns that we're interested in. Are they stable? Do they fluctuate? If they do, if these fluctuate significantly, then the asset is said to be volatile. Otherwise, it is not volatile. So this position expresses our view that this asset will remain not so volatile or maybe stable during the lifetime of these options. Now you have to ask yourself, what if we have the opposite outlook? What if we think that the option will actually bounce around quite a bit and will be very volatile? What can we do to make money from our belief? So what you're going to see here is that we're going to reverse the everything. So we're going to just work everything backwards. In fact, I could even save some time by copying and pasting and just making the appropriate changes. We're going to sell the low and strike calls in this case, and then we're going to buy the two intermediate ones. And so the result will be the graph will be flipped upside down again. And let's see what it looks like. Oh, now look at that. You can see that here we're hoping that it doesn't stay at 50, the stock price. We want it to move up or down, but we don't care which one it is. That's the important thing. We want it to move up a great deal or down a great deal. All we don't want is for it to stay in the middle. Okay, so now this one is a bet on the direction. I'm not sorry, on the volatility, not against it, but on the volatility. We're hoping that it moves around so that it either moves way up or way down, and that will generate profits for us. So think of this as a bet on volatility. Oh, it does say that at the bottom. A bet on volatility, which means we're pretty convinced that the price of the stock will either move up a great deal or down. We don't care which one it is, as long as one of those happens. It stays in the middle, then we'll lose money. Actually, let me copy this into the slides real fast. I mean, not the slides, the notes. And again, if you look at it carefully, you'll see that one is just flipped upside down from the other. So whenever you take an existing position and then you reverse it by selling where you were buying and buying where you were selling, you're going to flip it upside down as far as the graph is concerned, and everything will work in reverse. Okay, so that's our butterfly and reverse butterfly spreads. And again, we could have done the exact same thing with puts if we chose to do so. All right, now combinations, again, this is the one where you have at least one of each. One call, one put. So the first one we're going to look at is a case where we do actually have one of each. We call it a straddle. So with this one, you buy one call and one put with the same strike price, asset, maturity. What does that get us? Well, it's going to remind you a little bit when you see it of the reverse butterfly spread because if you notice, we're betting on volatility again. In other words, we're hoping that the price either goes way up or way down. We don't really care which, as long as it goes up or down enough to generate a profit, because it is, after all, a very expensive position. So here, it costs $5. We need to cover that either on the upside or the downside. So if we're currently at 50, the price of the stock needs to go above 55 or below 45 in order for us to make money. So this is a bet on volatility. An expensive bet on volatility. The butterfly spread only cost $1, if you remember. This one costs $5. But guess what? With the reverse butterfly spread, there's a cap in our profits. Here, there is no such cap. If you look here, if this price goes up to 100, for example, that just keeps adding more and more money to your pocket. Or on the downside, if it keeps going down and down and down, there's no cap. So that's the trade-off. This one, oh, actually, it was $2. Sorry. This one costs $2, but there's a cap on our profits. This one costs $5, but there's no cap on our profits. So this is what we have to think about when we set up these positions. How much am I willing to pay for this, and what kind of benefits am I looking for? Now, of course, you can probably guess that if we have the opposite outlook, we're going to set up what's called a reverse straddle, where we sell them both. And of course, everything's the same again, the same strike, strike price, asset, and maturity. And you could probably also guess by now that you're simply flipping it upside down because you're reversing the two positions. And I'm not sure if I have graphing here. I might have to draw it by hand. Let's see. All right, that'll do. All right. You can see it is, in fact, the straddle flipped upside down. So you can see now we're betting against volatility. Now this one, because we sold both options, when we first enter into it, we're actually collecting $5. Not only is it not costing us a lot of money, in fact, if anything, it's putting money in our pockets. That's pretty interesting that we can set up a strategy and collect money at the same time. But here's the thing we have to worry about. If you look down on the bottom, there's no maximum loss. Okay, the butterfly spread definitely has a distinct maximum loss. We put $2 in our pocket when we set this thing up. Our losses are limited to $1. Right here, we put $5 in our pockets, but there's no limit to our losses. So this is a position for somebody who's willing to take on a lot of risk. Okay, so but with these options, there's so much flexibility. We can essentially set up any position we like. I mean, like I said before, the sky's the limit with these things. So anyway, let's see, how much more do we have here? Oh, that was it. All right, I figured as much. So we don't want to spend the whole night on option strategies, although it is a very interesting topic. It's time to move on to pricing issues. We need to understand how options are priced in a marketplace. So we're going to introduce an incredibly important development in the history of finance called the Black-Scholes model. All right, now the Black-Scholes model is to finance in some ways what relativity is to physics. It proved to be that important. Now, of course, it was invented by Black and Scholes, but also there's a third researcher involved with this project named Robert Merton. It's kind of an interesting story because these guys they're academics. So imagine here's Fisher Black at Stanford, Myron Scholes. I'm sorry, Fisher Black was at MIT. Myron Scholes was at Stanford, and Robert Merton was at Harvard. And so they're academics. They get paid mountains of money to teach one MBA class a semester, and do buckets of research. And so they're working on this paper. Black and Scholes were working on this idea for a while. And later on, Robert Merton joined the team. He happened to have an awful lot of knowledge of very sophisticated mathematical techniques that in some cases had just been invented within the last 20 years. And so he was very familiar with the mathematics that they needed for this model, all of which is coming ultimately from physics, by the way. And he helped him a lot with the math. And he also made it possible for this model to be generalized to other situations. So when finally the paper is ready and sent out to be published in 1973, I've been told by people who would know these individuals that Black and Scholes actually said to Merton, listen, you're just as much of a part of this project as us. We're very happy to call it the Black-Scholes Merton model. And apparently Merton just said, nah, don't worry about it. Just call it Black-Scholes. That's fine. He's a very, very humble man. Let's put it that way. But I think in Hull's book, he does call it the Black-Scholes Merton model because that's really what it is. And so they came up with this idea, and we're not going to get into the details until a later chapter, but to price European call options on an asset that has no cash flows. It was very restrictive. And so they wrote this paper. It was meant to be an academic paper. It was meant to be like interesting, but not necessarily useful. Like all academic papers, who knows who's going to pick it up and who's going to find it useful. But they later on admitted that they had no idea how important this would prove to be. They were kind of surprised, as a matter of fact. So they publish it, and all of a sudden it becomes clear to all the traders throughout the world that we have a way now of pricing European options, at least European call options. And that means we can suddenly start trading them where before that wasn't really possible. And so the volume of trading and options suddenly went to the roof because suddenly there was a rational way of pricing these options. So plus the math that they use to get the results is something that is really used in virtually all derivatives pricing models and to this day. It was something called, let me just sneak this in here somewhere, the Black-Scholes model was based on a new branch of mathematics that just literally came out in the late 50s called stochastic calculus. So again, we won't get into this too deeply right now, but what it basically did was make it possible to take derivatives and integrals, especially of not just functions of x, but random variables. Okay, and it really is a very complicated area of study. This branch of math was developed by a Japanese mathematician in the late 50s. By a Japanese mathematician named Ito. I don't remember his first name. And so sometimes this stochastic calculus is known as Ito calculus. Bell's book, I think he refers to it as the Ito calculus. Now, in mathematics, there is no Nobel Prize, as you know. You know, probably know the story, but there is something equivalent to it. I think it's called the Field Medal or something like that. And so Ito did eventually win the Field Medal, but he, I think he died soon after that. He was in his 90s by that time. So um, he did eventually get recognition for this. And so Merton was somehow familiar with it, and he's the one who thought this would be the best way to the model should be based on this Ito calculus. And it's a good thing he did because this Ito calculus made it possible for the Black-Scholes model to be extended to European options on other assets besides non-dividend paying stocks, which is all that it could do when it first came out. When that paper first came out, it was literally just meant for that one thing, European call options on non-dividend paying stocks only. So once this paper came out, everyone got really excited and they said, you know, this is really quite a breakthrough. And so a lot of research was suddenly dedicated to option pricing models. And so Merton himself actually wrote a series of papers in which he showed what you would have to do to extend this Black-Scholes model into, let's say, pricing currency options or, you know, stock index options or whatever it was, as opposed to simply European call options. Now, as it turns out, this framework not extended to some American options. Okay. But as you can probably guess, within a few years, researchers, which we will see in the next chapter, by the way, researchers developed new models based on the Black-Scholes framework. Price of American, but it's a very complicated process. Okay. But that took a few more years. But once that came about, suddenly it became possible to price almost any option in the marketplace. And so that's when option trading really took off in the United States. Prior to that, there were a small number of transactions each year, but it was very, very minimal. Now, like all models, the Black-Scholes model is based on some very, very restrictive assumptions. Like what? All right, well, let's take a look. For one thing, assuming that the return to the asset underlying the option is normally distributed. All right, well, that's not a dreadful assumption. It's not unusual for rates of return for financial assets to be normal, but there's a few ways in which returns tend not to be normal. So here's our old friend, the bell-shaped curve. The center is usually designated with the Greek letter mu. That's the mean of this distribution. The shape or the spread is designated sigma for standard deviation. So in principle, there's an infinite number of these um, normal distributions. The one that we're really interested in here is the so-called standard normal. Has a mean of 0 and a standard deviation. Okay. Now, what about rates of return of financial assets? How are they not normal? Um, Rates of return to assets differ from the normal distribution in two, let's say, two key ways. One thing Actual returns to assets experience more extreme results or more extreme outcomes, both high and low methods, than is consistent with the normal distribution. Okay. So in other words, you're going to see something like this instead of the normal. Black will be the normal distribution. We'll have red be the actual returns, and they're going to be more like this. Okay, so this is actual returns. And if you notice, there's more area in the tails, as they're called, and less in the center. Okay, the black, of course, is the normal distribution. And another thing, if you notice, the normal distribution is symmetrical about the mean, meaning that the left and the right hand side are mirror images of each other. Actual returns tend to be, we'll explain this in the negatively. All right, so let me show you that. It just basically means there's an imbalance in favor of negative returns versus positive returns. So you might have something like this. Here's the normal, and then the actual returns look something like this. So the probability of getting a negative return is higher than you would expect with the normal distribution. Okay. Now that's not a perfect graph by any means, but you get the sense that with actual returns, there's an imbalance where there tends to be more negative returns than positive, or at least more returns that are consistent with normality. So that means the Black-Scholes assumption here is a little bit off. It's not a terrible assumption, but it's not perfect either. Okay. Now, another assumption of Black-Scholes. Let me add this at the end as a summary. The Black-Scholes model assumes that returns, initial returns are so this introduces adversity. Imagine into the Black-Scholes model. Now, the next thing that it assumes volatility. Now, the volatility in an asset, as I've already mentioned, can be thought of as the standard deviation of its returns. So volatility in assets volatility refers to the standard deviation of its returns over time. Now, this volatility tends to change over time. Okay, in other words, it depends on what's going on in the market. Sometimes an asset can be quite stable, and other periods it can be quite unstable. And the Black-Scholes model is that the volatility remain constant during the lifetime of the option. And then I'll discuss how that affects results. That's probably the one that's the most troublesome. Then we have number three, the risk-free rate, which is nothing but the yield with the same maturity as the option is assumed to be a constant during the life of the option. Now, that is not a terrible assumption. Interest rates, well, it's not that they never change, but tend to be stable. So this assumption is not necessarily a bad assumption. That could very well be perfectly true. The rates don't change very much, if at all, during the lifetime of the option. Okay. Okay, those are the important ones. Now, um, so in spite of all these issues, the Black-Scholes model has been used ever since it was introduced in 1973, or 50 years later. So it must be that this is a very useful model, and that's really, when you come right down to it, all that matters. Okay, there's a very famous economist named Milton Friedman who said something to the effect that the validity of a model depends not on its assumptions, the prediction, sorry, the accuracy of its predictions. That's what it was. Okay. I might be able to find a quote here somewhere. Um, I'm just out of curiosity. I'd like to see the exact quote, but this is going to take a while. Yeah, I give us the quote. Well, I maybe we're not going to find it. Oh, here it comes. All that matters is the accuracy of the theory's predictions, not whether its assumptions are true, or at least that's a paraphrase of it. So he was a very famous economist. He did win the Nobel Prize, but he was famous for a branch of economics called monetarism, which basically showed that the best way to manage the economy is to focus on the money supply rather than tinkering around with it or changing tax rates or all of this and that. He felt like that is all you really need to do is focus your attention on the money supply. But he was also very famous for being a hardcore libertarian and thinking, explaining to people how government typically makes things worse when they get involved. But anyway, let's see. Yes, so as I mentioned before, the model was extended by Merton to price other types of assets. By the way, the one thing we haven't mentioned here yet is this. What about puts? The Black-Scholes model was designed to price calls. What about puts? Well, it turns out there is a method that can be used to derive price of the put from the price of a call with the same features, meaning asset, um, maturity date, and strike price. This method is known as call parity. And we will go over that, just not right this minute, okay? So that made it wasn't necessary to have a separate model for puts, which really is helpful. All right. So in other words, once we know the call price, we can turn around and derive the put price with this methodology we're going to see later on called put call parity. So that accounts for the puts. So even then, at the beginning, all we had was the ability to price European calls and puts on non-dividend paying stocks. That's it. That's all we could do. So it was Merton who extended it out to other assets like options on currencies and other types of securities. But as I said, also said that the American options had to wait a little bit longer for a different framework that we could use that was actually consistent with Black-Scholes assumptions. But we'll get to that later on in the next section, actually. Now, this is the basic formula. So let's take a look at it. And it doesn't look too complicated, but if you could see their paper, and this equation ultimately comes from a result in physics. So they had to be very familiar, Merton at least was very familiar with the mathematics of physics. So he could actually say, listen, let's try this approach. What you're seeing here is the solution to a differential equation. And so we're not going to get into those details just now, but that differential equation is used in physics to explain the way heat is transmitted across a wire. So it's kind of interesting that you can use the same differential equation to determine how fast heat disperses across a wire and to price an option. So this is one of the reasons, by the way, why so many physicists work on Wall Street. They know the math intimately. They just didn't know the applications to physics until they came to the job and they learned it. So, so what do we need to know here? Well, first of all, C is the call price. S is the asset price. X is the strike price. R is the risk-free rate of interest. T is the time to maturity. Or the maturity. Let's put it this way: time to maturity of the house. Now, the other two parts, N and D1 and D2. D1 and D2 have separate definitions. They're listed separately because they're kind of messy. Yeah, you can see what I mean. So this is D1. And we also have D2, which is just derived directly from D1. Now the ends are taken from the normal distribution. So n is a function, as you can clearly see. And D1, for example, is this. Here's our normal curve. Now, this is the standard normal distribution, by the way. Which means it's a special case where the mean is 0 and the standard deviation is 1. So if, let's say, D1 is here, the ND1 refers to the shaded region, which in turn can be interpreted as the probability that Z, which is our standard normal random variable, is less than or equal to D1. So think of it as a cumulative probability. Okay. And then D2 ND2 is a similar idea. So they're both nothing but cumulative probabilities. Okay, and so there's your model. Now, ND1 and ND2 actually do have economic interpretations. So ND1, think of it this way, is the um, partial derivative of the false price with respect to the stock's price. Remember the symbol for partial derivatives. Um, now, the reason why it needs to be a partial derivative is because the options price is based on the stock price or asset price, the strike price, the volatility, the time maturity, and the R. So therefore, that means that when we calculate this, we're holding all the other variables constant. And this has a specific name in option pricing theory. This is referred to often as the options delta. Now we're going to see more of that later on in this chapter. But you can think of it as this way. If the stock price goes up by $1, what does that do to my call price? Okay, so again, it's a partial derivative based on the relationship between the call itself and the stock price underlying it. And so this is what it means. Then ND2 is, you can think of it as the probability that the option finishes. And the terminology we see in the options markets is about money. Or think of it as a positive payoff. Okay, so that's how we interpret those two ends. They're both probabilities. One is a probability. Actually, I'm sorry. One is a sensitivity measure. The other is a probability. Okay. So what we're going to do here is we're going to actually use the Black-Scholes model just to get a head start on this. We're not waiting until we go over VBA. I've set these two spreadsheets, these two Excel spreadsheets, so we can see how this is done in Excel before we attempt to do this in VBA. So I've got two examples coming up, which are taken from the slides, by the way. One of them is the original Black-Scholes model, and the second one is the extended version by Mert. Okay, so this is what's coming next. Now, looks like we're pretty much out of time here. So the next time we meet, what we're going to do is start right here. We'll go through this example, and we'll see how Excel calculates these numbers. And then we're going to see how that ties into VBA, because VBA in a lot of ways is very similar to Excel, but there's some very important differences. Okay, I guess this part can wait till next time because you don't want to rush through it. That's for sure. Once that's done, what we're going to do. Oh, we're going to look at the adapted or updated version. And then we're going to introduce the protocol parity condition. We're going to show why it must hold. It turns out that this relationship is enforced by the principle of no arbitrage. That if this fails to hold, there will be arbitrage opportunities in the market. So that we can save for next time. And then in part B, this one I actually had to break up into three parts. I'll quickly introduce you to a set of measures called the Greeks, of which delta is one of them. And they're all measures of how sensitive an options price is to different factors. Okay, so that's what we'll do next time. Okay. So anyway, I guess I'll see you then. So good night.